Hi, everyone. Thanks for joining us for today's webinar by Josh Silva. So this webinar is part of a series of webinars that we'll have to show outcomes of the Australian Characterization Common at Scale project, the ACCS, that was co-funded by the ARDC. In particular, outcomes from work package 4 on big data, electron and qualitative microscopy from experiment to publication. So very quickly, a brief background for Josh. So Josh has a career in IT, and he joined the ACCS in 2020. He works at the University of Wollongong, and there he assists researchers, IT personnel, and cryo-electron microscopy experts to explore and generate solutions for all of the various challenges that they may have around cryo-electron microscopy and the massive amounts of data that the instruments can generate, so that it has challenges in terms of transfer and storage. And Josh today will present us some of the results, some of the things that is developed as part of the ACCS project. So Josh, the floor is yours.
Hi everyone, and welcome, and thanks David for setting this up, and also for that that fancy title. It's much better than making stuff go faster or whatever I might have come up with, which is kind of the whole game, but putting some nice fancy words around it. Okay, so who am I? Well, my name's Josh Silva, as has already been stated by David. I'm working with the cryo-EM team here at University of Wollongong, or just UAW, as we'll abbreviate it to, just because it's a lot easier to say. I've got about 27 years of IT experience. After high school, I did some computer science here at UAW before getting a job at an internet service provider. I was there for 14 years, pretty much doing everything from support to server admin and even network design. Most of our servers were running FreeBSD, that's the little red icon. And just to make me feel old, we were pretty much running 33 6K modems at the time. 56K ones were fast, and Windows XP was new. I know there's people that have been around longer than me and consider that not that old, but at least for me, it makes me feel old. After that, I moved into the education sector. I did a brief stint at the University of Canberra before joining UAW. And I've been at UAW for about 12 or 13 years now. I spent the first 10 of that in the desktop support team as their Mac specialist. This was a role I kind of inherited at University of Canberra, given that OS X at the time was pretty much the same as Linux and FreeBSD. It just had Apple's GUI on top. But yeah, I was very familiar with all the stuff that happened underneath, so I kind of just got put into that role. And then since 2020, I've now been on a secondment with the cryo-EM facility here at UAW as part of the ACCS project. And I've been helping them with data storage and data transport and optimizing workflows. We use mostly Linux servers here. And I've been helping with, basically the install, software updates, all those sorts of things. It was also a good fit for me because a lot of the researchers tend to be Mac users, so I already knew most of them just from being in my support role. So when I came over here, sort of like moving in with a whole bunch of people I already knew. It does give me a unique position because I've come from that central IT background, and I know how a lot of their policies and a lot of their systems work. And I am also now sitting, in sort of the facility IT role where I have like direct interaction with the researchers. So we have lots, actually, can I? Yeah, there we go, sorry. we have lots of data that gets generated here, massive sizes that a lot of the central IT's policies and systems were just never designed to cope with. So, while they might have a policy that says we do something with research data, and in an ideal world, that might be great. Systems that were designed for maybe a couple of gigabytes or maybe a terabyte worth of admin documents, they just don't cope with the massive data sizes that cryo-EM produces. So we end up sort of skirting the edges of some of the things that they would like us to do, and knowing the right people, or at least the right team to approach, along with what we're trying to actually achieve here within the cryo-EM facility, has allowed us to achieve some of those outcomes a lot quicker than we might have otherwise been able to. There we go. So I'm also going to touch on what I'm not. My background's IT. I'm not a scientist or a researcher. I do work with them. I did marry one. And, this talks mostly about the IT that sits behind the research. So yeah, that's hopefully not too much of an issue. I'm also not great with presenting or keynote. It's not sort of my standard thing. I'm not a lecturer. I did have a bunch of animations where these little icons would kind of pop in as I talked about them. Couldn't get them to work properly. I'd click the next button, I'd get 2 of them, and would skip to the next slide instead of the next little thing. So I ended up pulling all of that out. So it is what it is. And I also don't necessarily think of myself as a developer. I have done some comp-sci. It was decades ago. I can read code, I can make scripts. There's no problems with any of that. But I'm not in touch with all of the latest, best practices. It's not my, main role. So, the code is available on Git at the end. If anyone's looking through it and knows a better way to do things, please let me know. So what we will be covering today is basically UOW's journey towards what we've termed near real time. And allowing the researchers to assess the data that's coming off the microscopes pretty much straight away. I'm going to be basically talking about the cryo-EM facility and cryo-EM data, but basically these challenges that we've had and the solutions we've come up with are pretty general. They'll work with any data generating instrument. It doesn't have to be specifically cryo-EM. I'm going to start with a brief background, sort of bit before I joined the team, how things were before automation and some of the stuff that we've done. This is basically just to set the scene, but also to give us a reference point to compare, where we were and where we are now. I could just talk about what we've done, but without that historical viewpoint, it sort of, doesn't sound as impressive. I did have to obviously ask a bunch of questions to find out a lot of this stuff because it was before I joined the team. I don't have any firsthand knowledge of how things were done. And I was a bit surprised when I started asking that some of these very simple automation steps were actually only relatively new. They, I thought they'd been in place for years and years, and that wasn't the case. So it's, interesting to see how far we've come in a very, very short time frame. So yeah, so there's been a lot of technology advances. Technology advances very quickly, and this has been, I suppose, good and bad. Some of those advances have allowed us to rethink the way we do things and move our goalposts. Some of the advances have pretty much left us with no decision other than to rethink how we do things and move those goalposts. And I'll be covering off on the major steps that we've taken along the way, what our pain points have been, and hopefully this will help others that are wanting to go down, to follow what we've been doing, and know where our troubles, have come from, so that they're at least aware of them, and hopefully they can avoid them themselves. We'll look at where we are now, or at least as of yesterday, and I'll I've added a little asterisk to the slides later on, which I'll touch on when we get there. We'll look at how future-proof things are for the near to mid-term. And then, in an ideal world, in the future, where would we like to see ourselves and this process? So just for reference, this is a rough diagram of our data workflow. And we're going to be looking at mostly steps B and C here, from when the images land on the capture PC, get transferred across to our central storage, and are then accessible from the local compute to start providing those results back to the researchers. I will touch briefly on a few of the other steps, but they're not the main focus for today. I've also got no idea why that end of workflow is truncated. It looks fine in the original, just doesn't seem to work in PowerPoint, in Keynote for whatever reason. So at the start, this is the Titan Krios that we have arriving. This was early 2018, and it was while the Molecular Horizons building, which we're in now, was still under construction. So initially the microscope was set up off campus at a place called ANSTO, and it was commissioned in August of 2018. So we had two smaller cryo-EM microscopes on campus, but if you wanted to use the fancy big new one, the Krios, well, it wasn't quite as simple as we would have liked. The microscope, the capture PC, and a storage server for it were all located at ANSTO, which was about a 45-minute drive away from campus. So once you had your sample ready, which was prepared here on campus, you'd have to then drive across to ANSTO with your sample. Now I'm guessing most of this live audience probably know what ANSTO is, but it's the Australian Nuclear Science and Technology Organisation. And that N, the nuclear part, that makes getting in there, a bit of an issue. You couldn't just, rock up at the gate with your sample. There was paperwork and processes in terms of, getting access to where the microscope was. So you sort of, when you went to the microscope and you went through all of this, it was pretty much a day visit. You'd go up there, you'd spend the day getting the samples loaded, making sure the microscope and the detector and everything was configured. And then before you left, you'd start your data capture. So once the data capture was running, there was still a few issues. The next one was the vendor supplied PC that drives the detector. This is kind of a step A in the diagram before. It's the images coming off the microscope land on the internal drives of this machine. And it's pretty much a little black box. It's vendor managed. We've got a few little things we can do to it, but we don't have much scope for doing things like, upgrading the storage capacity, for instance. So the drives in this machine weren't terribly big. If you left it running, it would fill up within 24 hours. So any data capture runs that were going to go longer than this were a bit of an issue. We did have remote access to the machines at ANSTO. So if it was going to be a longer data capture, someone would have to connect to a remote desktop connection onto the machine, manually drag the captured images across to the file server to free up space, and then you could kind of resume the image capturing. There was no automation at this point. It had kind of only just been set up, and it was all very, very manual. And then once the data capture was finished, I'd have to go back up to ANSTO with some USB hard drives, copy all the data onto those, and then bring them back to campus via what we called SneakerNet. So again, all of this just takes time. Once you had the hard drives back, you'd have to transfer those again onto local campus storage, or sometimes down to Massive, our partners in Melbourne, for the remote HPC compute, depending on the data and where that was going to happen. So once you finally had access to the data, you could then start to do your screening, work out if your samples were any good, if the microscope settings were the ones that you're after. And when all of that was done, basically you were crossing your fingers and hoping that everything had worked the way you're after, or you were back to the start. and had to go through that process all over again. So that obviously, wasn't an ideal way to run things. So there were a few quality of life things that were done pretty quickly. First one was that central IT here was engaged to provide an automation script to basically automate the moving of the images arriving on the capture PC over to the storage server. Excuse me. So the capture PC runs on Windows, and at that time the storage server was a Linux box. The facility's preference was to run what we call a pull script, where it runs on the file server and pulls the images off the capture PC onto the server. However, the central IT people that were involved at the time were all Windows admins, so they came up with a push script which runs on the capture PC and pushes the data across to the storage server, because that's what they knew how to do. It wasn't the solution we were after, but it was a damn sight better than the remote desktop and manually copying things along. The drives didn't fill up anymore, and the images were just on the file server waiting for us when we got there. I also don't know the exact date, but there was also a network upgrade to the link between UAW and ANSTO, which meant that we could retire the USB hard drives and sneakernet. We could now just download the images direct to campus. It was still slow. I don't know whether it was actually that much faster, or if it even was faster than sneakernet, given the volumes of data, but it was, again, a lot simpler. You didn't have to go anywhere. You could just click go, come back tomorrow, or whenever it happened to be that the transfer was finished. And it just simplified the whole process. And then finally, in late 2019 and early 2020, the Molecular Horizons building was finished. And with a few delays, because of COVID was now a thing, we were able to get the Krios microscope relocated back to the UAW campus. This was also about the same time that we were playing with CryoSpark Live. It was just a sort of, I suppose, a bit of a demo at that time. But what it meant that, in conjunction with all of these other updates, that instead of being days or sometimes weeks before you could see the results of the images coming off the microscope, we could now get that down to tens of minutes, maybe an hour or so, which was, obviously a great improvement. Being able to know, sooner whether things are working the way wanting means that you can either, let things keep running if everything's working great, or you can, make changes to the microscope if you need to, change the sample, all those sorts of things. And, you knew before you wasted days and days of, microscope time. So this was just the initial screening, before you sort of did the full data capture. There was still the longer either local or HPC compute that was required at the end to get the full results, but at least you could tell whether you were getting useful data or not. And this is where I joined the team. The basics were in place. We sort of had this stuff up and running, and yeah, that's when I came on board. So by sort of mid to late 2020, CryoSpark Live was now a crucial part of our data workflow, and we were looking to move the goalposts. I was up to speed on a few of the things and how everything worked around here, all the servers and the network layout and the workflow processes and all those sorts of things. So we were looking at what we could do to improve the performance. COVID was pretty much in full swing. Like a lot of the rest of the sector, UAW was tightening its purse strings. So we had to look at what we could do to improve things with our minimal, cost investment. And the obvious place to start for us was the initial script that was provided by Central IT. So when that got written, performance wasn't one of the metrics that was ever thought about or, designed for. It was mostly to stop the hard drives on the capture PC filling up. So it did its thing, it worked, but there were some timings in there and some delays and things that were, erring on the side of being cautious to make sure that everything worked rather than, how quickly can we do things. So the script was called by Windows Task Scheduler every 10 minutes. And it ignored any files that were less than 10 minutes old. This was to stop copying a file that was still in process of being written to disk. Okay, so there was plenty of scope there for us to try and reduce some of these times. 10 minutes was very generous on both of those fronts. When we started looking at some of the data sets and checking the timestamps on the images coming off the microscope, it was only about 45 seconds between images. So that would be like the worst case of how long it took to write to file. I don't know that it actually took that long to write the file to disk. I'm sure some of that was just the capture and processing time. But we decided that there shouldn't be any problems dropping those 10-minute times down to say 3. It gave us a little bit of safety room just in case something took longer than we expected, and definitely sped things up. So we changed both. We changed the scheduled task to 3 minutes. We changed the how long it ignored those new files for down to 3 minutes. And we're thinking, brilliant, we've just saved ourselves bucket loads of time. This highlighted a few other issues that we had. And the main one was that the capture PC had never been set up to sync to a network time server. All of our servers did, our file servers, our GPU machines, so they're all nice and neatly synced up. But we discovered that the capture PC, its clock had drifted. It was out by about 5 minutes. So you never noticed when timings were at 10 minutes, but when we're now running things every 3 minutes, we noticed that its clock was affecting, all the timestamps on the files, and things weren't happening as we were expecting. So we fixed that one up, and yay, it was all working. We hadn't done anything special. There was no real, costs in terms of new hardware or anything. We changed 2 numbers, one in the script and one in the scheduler. And that feedback loop for researchers had dropped from about 20 minutes. It was now about 6. So the other way I suppose you could think of that is we'd improved it by a factor of about 3 times. We also found that in practice, having a 20-minute delay there, it was just long enough for someone to sort of go, oh, you know what, I can go and do this other thing that I need to do quickly while I'm waiting. You then get sidetracked. The phone would ring, you'd answer an email, you'd get stuck with whatever it is that you were doing. And often it would actually be, maybe closer to a couple of hours before someone would actually come back and check how things were going. When this was dropped to 6 minutes, basically it wasn't very long at all. I suppose if you were really quick, you might be able to go and get a coffee or something like that. But otherwise, most people would just sit there and wait a couple of minutes. So it also had those other effects that were not necessarily just about the how quick the scripts were running. I can't remember exactly when we started using the term near real time, but it was definitely in use from this point onwards. So hopefully this is something that others can find helpful as well. It doesn't always need to be expensive hardware upgrades to make things go faster. Sometimes just revisiting what's in place already and looking to see if you can optimize things, will get you the results you're after. We did do hardware updates, new GPU machines, new file servers over various time points, but the speed ups from those were all incremental. Things were pretty much fast enough as they were. So that ran fine for close to a year. It just chugged away and did its thing, and everyone was happy. We got to the end of 2021, 2022, and some upgrades were done. We got a new detector on the Krios. We went from a K2 to a K3. It's newer, faster, more pixels, higher frame rate, all those other good things. To go along with the better detector, it needed a new capture PC. So this was again still vendor supplied, but upgraded, a bit beefier. And then there was a new version of the software, and it gave us a whole bunch of extra features that we were interested in as well. I haven't really touched on it here because it's not, I suppose, overly relevant to the real-time processing, but we were in the background doing MRC to TIFF compression as an extra step of our workflow. We were getting about an 8 to 10 times space saving when we were converting the MRCs to TIFF with compression. It was lossless compression, and this new software had the ability to do this at that point of capture, which would simplify our workflow a little bit. We didn't have to spend, hours of CPU time after the data had been captured and transferred to our file server, then going back and recompressing all these images. It also meant that the data transfer off the capture PC would remain about the same. The increased volume of data coming off this new detector kind of balanced out with the data compression, so that we were still transferring about the same amount of data, per day, per hour, whatever sort of time frame you want to think of it. So the rest of our workflows and our network links and all that stuff wouldn't really be impacted too much. And just like when we changed the timings on the copy script, these upgrades and the fact that we did kind of all of them at once highlighted some places we could have some improvement. We found that the data captures were crashing, not straight away, but within 12 to 24 hours, sometimes less, the data capture would just crash. And trying to track down where that issue is coming from when we've changed just about everything meant that we had to do a fair bit of testing. We could run the capture and the compression to TIFF just fine. We could capture to the old MRC, like the non-compressed format, and run the transfer script just fine. But if we tried to capture to TIFFs and run the transfer script all together, this kind of seemed to be the issue. And when we started looking at things, when the transfer script was running, and this was still the push script running on the capture PC, it was using about 20% of the CPU time while it was running. It was, obviously checking all the date and timestamps on the files to see whether they were too new and it had to ignore them or not. And then under the hood, the script uses a thing called rclone for doing the heavy lifting, and it was running multiple parallel copies to sort of get the speed that we were after. So that's where the CPU usage was coming from. We did try turning down some of the settings on the script. So rather than using 8 parallel copies, we tried dropping that to 4 or even 2, but it didn't really affect the CPU usage. We couldn't go below 2 threads because then the transfer speed was too slow, and we're actually filling up the drives quicker than we were emptying them, which would mean that over time the drives would still fill up. So this was when we decided that, yep, we have to switch back to, and have another look at running a pull script instead. This has always been, what we've been pushing for. It had never, made it to the top of the to-do list because the current or the existing setup at the time had previously been working fine. The idea was simple enough. We could take the existing script that we'd been given by Central IT. I'd spoken to the original people that had written that, and they had no problems with us taking it and rewriting it. Converting it to Python to run on a Linux box wasn't going to be an issue. rclone is multi-platform, so you can get Mac, Windows, Linux versions of it. And we used it elsewhere. I quite liked it. And it was all command line based, so it was really easy to pop into scripts and to tell it to do things. Supports parallel copies. It had heaps of configuration options. So, we went ahead with looking at that. But we had to do a few things first, just to check that it was actually going to work. So we set up sharing on the capture PC. It had in the past mounted a share from the file server. We were now flipping that around. So we set up sharing on the capture PC and connected to that from one of our other boxes. so that it looked more like this. We had a box sitting in the middle. It had access to the storage server. It also had access to the capture PC, and we were running the copy from there. We did a manual test first, just to make sure that things were going to actually, make a difference. And we found that the CPU usage on the capture PC dropped from 20% down to about 2%. We hadn't got rid of the CPU usage. It was just now a different machine CPU, not the capture PC. It was still a single move operation. The data didn't land on this machine. It just had 2 network shares and was moving data from one to the other. So it looked like it was all going to work. So this is basically, we get to where we are now. With those, tests done, the script was rewritten in Python. It's been running now for a couple of months and is working well. While we were doing the rewrite, we improved a few things that we'd noticed when we were, just doing some of our changes earlier to the original script, both to improve things and also just to make it more versatile, because we, had plans of reusing this script elsewhere. So the original script that we were given had a config file, but the only things in there really were the source and destination settings. A lot of the other settings, like how many parallel transfers to use and the ignore time for when to how old the files had to be before it copied them, they're all hard coded into the script. We could go in, we could find them, we could change them, but it wasn't quite as easy as just changing a number in a config file. And we also changed it so that the script can accept a list of source and destination locations rather than just a single source and destination. And we can also give them each their own copy settings. So if we do have multiple folders for different things, we can set up a separate copy for each of the folders. The main reason for this was that the K2 detector that was on the Krios was now being shuffled down the line to our Telos Arctica. So we'd have a second machine that we were running to run this same script on. And we're probably going to run 2 copies of the script anyway. That way we can sort of stop one independent of the other one if we ever needed to. But if we chose to, we could have the one script running and doing a copy from one microscope onto our file server, and then the other microscope onto the file server, and have the one script doing that. The other thing for us is that now that it was on a more familiar system on Linux, which, well, at least myself, I know better. I'm not really a Windows person. It meant that I was more familiar with some of the things that we could do. Windows Task Scheduler may be able to do some of these things that we changed. I just don't know whether it can, and it definitely wasn't the way it was set up. The big change that we did make using Linux's system control, which is kind of its task scheduler, is rather than being on a fixed 3-minute trigger where the script would just run every 3 minutes based off a real-time clock, we changed it so that the trigger was now 3 minutes after the last iteration had finished. It did push out the time between iterations marginally. Basically, you added the time that it actually took to run into that, but it also eliminated some of those sort of gray areas that we weren't quite sure what would happen if something happened and the next iteration triggered before the previous one had finished. We never really got around to testing what happened. We weren't quite sure. Maybe, if there was a network issue or something and there was a backlog of images, we kind of just manually did that before we turned the script back on. But this way we knew that even if there was a network issue and the files weren't copying, we could just turn the script back on. Yes, that first one might take longer because there was a backlog to clear, but it wouldn't trigger a second copy until 3 minutes after the first one had finished. We also noticed that we actually were getting much better network performance. The push script, when it was running on the compute PC, had what we call a mark space ratio of about 60%. So it was running well, initially every 10 minutes, and it would take about 6 minutes to copy those files. And that was pretty much the same when it was running every 3 minutes. It would take about 2 minutes to copy the files off. So there was a bit of a gap before it ran again. But now with running things from the Linux machine, that had dropped down to about 10% of the time. So it ran for about 20 seconds. And then there was, that was out of sort of 3 minutes and 20 now. So that was something that we weren't expecting. None of the network links had been changed. No real hardware changes or anything like that, other than that we were using a separate machine, but it was still on the same network. It still had the same network links. This looked great at the start, but faster isn't always better. We'd solved the CPU load issue by offloading that, but potentially created an I/O issue where we were now reading things super fast off that capture PC. Our clone does have the option to add bandwidth limits, but for now we haven't noticed any I/O issues. But if we need to, we can look at that. So I've added a little asterisk next to the more stable. That was until yesterday. We did have a crash yesterday. Thinking it might be related to the MRC to TIFF compression plugin that the vendors supplied rather than necessarily our script. Going to do a little bit more testing on this. It is only a one-off. It could have been a one-off, or maybe our initial tests, we just didn't run them for long enough. And yeah, we'll see how that goes. But for the most part, it has been more stable. I've also got a to-do list of just little improvements that will be added to the script. The basic functionality is there. As I mentioned, I'm not a developer. I do want to add in some better exception handling so that if things don't work as we're expecting them to, that the script can, handle that, flag them, log them, alert us to it, all that sort of stuff. So yeah, just brushing up on what is best practice and the best way to do those. And also adding log management. It's writing logs at the moment, but have a way to clean them up. Keep a week's worth of logs. We don't need to really go back further than that. We'll know pretty soon if something's not working. Okay, so looking into the future, how future-proof is this? Well, we've now got plenty of bandwidth I/O in terms of network I/O available. We're down to about a 10% mark space ratio. So if in the future we do get an even better, faster detector that's generating more data, if it happens to be something, like 4 times more data, better frame rates and all that stuff, there's still plenty of capacity to move more data. So that one shouldn't be an issue. There's also the option to tighten up some of the timings. The 3 minutes is some numbers that we came up with the old detector and the old system. We'll try and work out where this if this crash is coming from the TIFF stuff or not first. But once we get that solved, we can look at the timings on how often those TIFF files are created. Is it less than the 45 seconds? Can we speed things up there? Can we make that 2 minutes or 1 minute and reduce some of the times there? We should definitely be able to reduce the delay between how often the script's triggered. You'll generate a few extra log files, but that's about it. We can easily drop that 3 minute delay down to 2 or 1. And can we also drop the ignore time? The big problem, at least that I can see, is probably the performance of the capture PC. It looks like it's already running pretty close to its limits. Obviously, when we got this new detector, we got a newer upgraded capture PC. So if that was to happen again, we'd probably end up with a newer upgraded capture PC to go with it at the same time. But yeah, that's probably the biggest constraint that I can see at the moment. So any any other upgrades that we're looking at doing, you know, to the script and things like that, we'll need to try and minimize the amount of strain that they put on that machine. And then ideally, you know, in an ideal world, what would be the holy grail? Where would we like to see things, you know, well into the future? And, you know, we've had a few discussions about this. No script at all would be great. What we'd love to have happen would be to have the file server, like a share from the file server, mounted directly onto the capture PC, replace basically the internal drives with a network drive, and just have it saved directly to the file server. Get rid of all of those delays altogether, and make the files accessible to the GPU machines the second that they're saved. Few issues with that. The basically network reliability. If the network goes down at the moment, the script stops, but the data capture keeps happening. It just saves to the local drives, and it will keep doing that for a little while. And you know, if it's saving directly to the file server and the network goes down, what's going to happen? Probably going to lose data. Cryo-EM is a destructive thing, so you'll probably lose your sample as well. So they're things that we need to keep in mind. And also the fact that at the moment there's no vendor support for doing things that way, if it could even be done. But you know, that's a maybe one day kind of thing that we'd like to work towards. So that basically brings us to the end. Thanks for listening. There's a few links here. One to the GitHub for where the code for the script is. It will be getting updates shortly. There's also a link to rclone for anyone that's wanting to check that one out. It's the part that does the heavy lifting, does all the copying and the transfers, and it's, you know, at least in my opinion, a great little tool. And then lastly, there's some links to the reports that I'll be doing for my work here in the ACCS. These are just placeholders at the moment. The reports will be added in the next month or two.
Thank you, Josh, for this talk. I think there was a lot of information that could be very useful to many facilities, not only microscopy, I guess all sort of instruments, in particular those that generate a lot of data, and when a facility has to manage that both for capture and transfer to storage or compute. So thank you, everyone, and see you in the next webinar. Thanks, Josh.
Not a problem. Thank you.